in part E of module 3, linear recurrence relation. Why we need to do this? The reason is very simple, because the question, how do we discover the Fibonacci formula? Last time we verify it, but when we verify it, someone needs to find it for us, okay? Yeah. So we bypass the discovery step. Yeah. But in the real world, when you need to find a brand new formula, so nobody knows it before, so you have to discover it. Yeah. Here, this last topic, we will learn a systematic method to solve that linear recurrence relation. Yeah. This topic you have learned in discrete math, but here I just go through it another time. Yeah. So I hope in this time you can completely master this method. Yeah, very basic. Yeah. So let's start. First, let's look at the problem first. Yeah. First, let's try to understand the official name of this recurrence relation. Yeah. Yeah. Look at this recurrence relation. Yeah. A very simple one, but there is an official name for it. So what is that official name? Yeah. Look at this long name. Second order linear homogeneous recurrence relation with constant coefficients. So long. Yeah. This long. Okay. Yeah. Second order linear homogeneous recurrence relation with constant coefficients. Let me explain why it has such a long name. First, it's a second order. So why second order, not first order? Yeah. Second order, look at the right-hand side. There are two terms. Two non-constant term. Two non-constant term, right? Yeah, yeah. The second order, yeah. If we need to compare, in order to understand the second order meaning, we may like to compare with our old example. Yeah. Remember, in the old example, there is we learned one called that Tower of Hanoi. Remember that problem, that puzzle? Yeah. In that one, we derived, yeah. Oh, just a minute. That one derived that. Probably I skipped that. Yeah. Yeah. So later sometime I will bring it back. Yeah, because in that Tower of Hanoi, we have a simpler recurrence relation. So that is Cn equals 2Cn minus 1 plus 1. Okay, so here you can see at the right-hand side, there is only one non-constant term. And for this type, we call the first order. Okay, yeah. Here, right-hand side, we have two non-constant terms. So we call the second order for its name. Okay, yeah. Linear, yeah, to understand the linear, so you can see each term is a linear term. No square, no, so the exponent. So each term, the exponent is 1. Each exponent of each term is 1. exponent of each term is 1. So that's the linear term. Yeah. So that's the reason we call it linear equation. Yeah. They're homogeneous, this name. Why the homogeneous? Homogeneous, yeah. Look at this. Look at Tower of Hanoi example. Look at this +1 thing. +1, it's a constant. It's a non-zero constant there. Yeah. So this is non-homogeneous. Non-homo. Yeah, let me just write this. And look at here, the constant part, 0 constant. Yeah. For an equation, when the constant part is 0, we call it a homogeneous equation. Yeah, that's the name. So this one, we have that property, homogeneous property. Yeah. Recurrence relation with constant coefficient. So what do you mean constant coefficient? Look at the coefficient of each term. The first term is 1, it's constant. The coefficient of second term, also 1, also constant. Yeah. Because sometimes you may have a non-constant efficient. For example, n minus 1 fn plus n plus 1 fn minus 1. How about that? N plus 1. Okay? That is non-constant coefficient. Yeah, if you compare with that. But here, both coefficients are 1. So in order to cover all the properties for this type of equations, so we give this long name. Yeah, let me repeat it the last time. So that is the second order linear homogeneous recurrence relation with constant coefficients. Yeah. All right. Next, we need to solve it. Yeah. We need to use a systematic procedure to solve it. Yeah. Standard procedure. Yeah. All right. And we consider a general case, yeah. Not just this special example. Yeah. The general. Yeah. The general case, A sub k equals capital A constant capital A times A sub k minus 1 plus B times A sub k minus 2, with B not equal to 0. Because if B equals 0, then it becomes first order, not second order. Here, we only want to consider the second order. First order, much easier. So we do not worry about the first order. Yeah. Yeah. All right. And for the Fibonacci case, A, capital A and the capital B both equals 1. Yeah. So you can see that's the simplest case. Yeah. All right. Now, so let's go through the procedure solving this problem. All right. Before I run this procedure, I want to give you some inspiration. So why we choose this method? There is some good reason behind it. Yeah. So let's take a special view. Yeah. We try to find some rationale behind this procedure. Yeah. Consider a sequence. Here, let us consider the little a sequence. All right. And we like to guess some special pattern for this little a. Special pattern, guess. Yeah. In problem solving, guessing is very important. Yeah. Guessing, we try to, predict. Yeah. Guessing actually making prediction, right? Yeah, the guessing step is the prediction step. Yeah. When you make a good prediction, then you can solve the problem easier. If you cannot make good prediction, then it is much harder. Here, we want to make some good prediction. But for the pattern, so we may feel how, because when you make a guess, your guess has to come from some related information, right? Yeah. Because you cannot make baseless guess. So you have to provide some, evidence or some, based on some existing information, then you make some reasonable guess. Yeah. Here, we need to have that part. Yeah. When we guess a pattern, we need to find some good reason behind that pattern. Yeah. All right. So here, the pattern structure, we guess little a sequence should take this t to the k power function structure. Yeah. So this is a power function structure. Yeah. Okay. But you may wonder, so why, how do you know you should take the power function structure? Yeah. Here, let me give you the reason. Yeah. Look at the first order case. The first order case, Cn equals A times Cn minus 1. Let me omit the constant term. Yeah, we consider the homogeneous case. How about that? Yeah. Look at that. To solve this recurrence relation, very easy, right? Because the obvious solution, Cn, because you just do iteration, you can get equals a to the n. Yeah. Because from Cn minus 1, you can get Cn minus 2, right? You can get a squared Cn minus 2, and so on. Keep doing that, and at the end, you get Cn equals a to the nth. Right. That is the power function, right? That is the power function. So you can see the solution structure for the first order linear recurrence relation, homogeneous recurrence relation. That's the power function, the solution structure. Yeah. Now, when we move to second order, can we try the same structure here again, another time, right? Yeah. That's the, base information for our guess, right? Yeah. Yeah. So it's not baseless. So that's the base of our guess. Okay. The rationale. Yeah. Some good reason, reasonable reason for this structure. Okay. Yeah. So we take this power function, t to the nth. Yeah. T, what is the t? Yeah. You may argue, what is the t, right? T, unknown, and to be determined. How about that? To be determined. Here we do not know its value. Okay, to be determined. Yeah, we will figure it out. Yeah. All right. And we know the structure people also call geometric sequence, arithmetic sequence, and a geometric sequence. Yeah, but it is just a name. Okay, yeah. But now let us determine the t value. Yeah. But when we determine t value, for simplicity reason, we can ignore the initial condition. Yeah, yeah, because to avoid any complexity, yeah, so we just want to make our current problem as simple as possible. Yeah. So let's just ignore the initial condition. We only want to consider a solution for that recurrence, original recurrence relation. So let's plug in. Yeah. Let us determine that little t to give us just one solution, simple solution for the original recurrence relation. Yeah. So let's plug in left-hand side, AK, based on our assumption, it should be t to the kth. Yeah. Similarly, a to the a sub k minus 1, t to the k minus 1, and so on. All right? Yeah. Just solving this simple equation. That should not be too hard, right? Yeah, because only one variable, t. Yeah. So this equation, we should be able to solve it. Yeah. But the exponent part, not that easy. K unknown. Yeah. Can we simplify it? Can we make this equation as simple as possible by cancellation? We can do some cancellation. Yeah. All right. After cancellation, yeah, actually we do division by the lowest power of t to the k minus 2. Yeah. Do this division, both sides. Then you will get a very simple, we call quadratic equation, right? T squared equals t plus 1. Quadratic, simple quadratic equation. And in this equation, we're familiar with this equation. Look at that. So if we write it to the standard quadratic equation, you can see this t squared minus t minus 1 equals 0. We're familiar with it. Yeah, that's because we solved this equation before, remember? When we try to find the golden ratio, that is this equation, is x squared minus x minus 1. X is the golden ratio. Exactly the same equation, right? Yeah, just a variable, we use different variable. That's not important, okay? Using x or t, yeah, that's not very important, just a variable, okay? Then the solution should be, or at least the same way to find the solution. Yeah, because we have the quadratic formula. When we apply the quadratic formula, we can find two solutions. T1, the golden ratio, the familiar golden ratio expression, 1 plus root 5, whole thing over 2. Yeah. T2, 1 minus the conjugate solution, that one, 1 minus root 5, whole thing over 2. Yeah. So you can see we find two different solutions for the current quadratic equation. Yeah. Actually, we found the same two solutions when we try to find golden ratio. And because the definition of the golden ratio, so it's a ratio of the length of two line segments. We know it must be positive. So we drop the negative solution. Yeah, so that's the, golden ratio story. Yeah. But here, this little t, what's the meaning of this little t? The meaning of this little t, just one solution for the, that gives us a solution for the current recurrence relation. It has nothing to do with the golden ratio, right? From the definition, it has nothing, we do not interpret it as the golden ratio. Okay. And we do not have to connect it with the golden ratio, right? Yeah. Yeah. So that means the negative second solution should not be dropped. We should keep the second negative solution. Yeah, because we do not assume this T is the golden ratio. There is no reason that T cannot be negative number, right? Yeah. So that means these two solutions should be considered as valid solutions for the given recurrence relation. That's the conclusion. The conclusion is we find two different special solutions for the given recurrence relation. One, T1 to the kth, and second, T2 to the kth. Yeah. All right. So that's our first step. Second step. Yeah. Because that's two special solutions, right? Two special solutions. Now we want to consider initial condition. Yeah. Because for those two special solutions, we didn't consider the initial condition for the recurrence relation. That's not good. That means those two solutions won't be our final solution, right? Because definitely T1, T2, they're non-integers, right? T1 not integer, T2 not integer. When you raise to the kth power, still they are non-integers. That cannot be our Fibonacci numbers. Yeah. So our next thing is we need to really find a solution that satisfies the given initial condition. Because only when you satisfy the initial condition, then you can get Fibonacci numbers. Yeah. So we need to bridge that gap. Still, there is a gap there. Yeah. But we need to do some work to bridge that gap. Yeah. So let's see how do we complete that last mile. Okay. All right. So let's start with this one. Yeah. Yeah. So two solutions. These two solutions, we can make two special solutions for the given recurrence relation. Yeah. So that means if you plug in T1 into the given recurrence relation, you have that. So no problem, because we solve the equation from there. So now we plug in back, it must be correct. Okay. The second T2, if we plug in, we also have this identity, these two identities, okay, or equalities, correct equalities. Yeah. All right. The question, yeah, the next step we need to do, we need to find a new solution that satisfies the given initial condition. New solution. But this time we need to factor in the initial condition. Yeah. The question, how do we do it? Okay, yeah. With two special solutions, how do you make a new solution from two non-special solutions? That's our current question. Okay, yes. So to answer that question, we need to use some special technique in math. Yeah, special technique in math. Yeah. All right. Yeah. Yeah. So now, so consider our goal. Construct, let me write our new goal. Okay. Yeah. New goal, okay? Construct a new solution from two special solutions. That's our current goal, okay? Yeah. The question, how? How to do that construction, okay? Yeah, all right. The construction, so here, there is a simple idea in math, very simple, yeah. But if I do not show you this simple property, it's hard to imagine the simple construction way. Yeah, the construction is very simple. Yeah, all right. So let me go there. Yeah, the question, how to use two special solutions without the initial condition to get a new solution with the initial condition. Yeah, so that's what we are going to do. Yeah, we need to take advantage of one special property of the given recurrence relation. One special property. Remember, at the beginning, I gave you the long name of the recurrence relation. Yeah, one of the properties, because that long name covers several properties of this equation. Here, we just want to take advantage of one of the properties there. Yeah, so let me repeat that name again, long name. Second order linear homogeneous recurrence relation with constant coefficients. All right. In that long name, there is one word called linear. Linear. This property is useful here. Here, we just take advantage of this useful property. Linear, that gives us the property called the linearity property. Linearity property. We want to take advantage of the linearity property. Okay? Yeah. To do the construction. Yeah. So here, construct. Do this construction. Okay? Take advantage of the linearity property. Yeah. How? Yeah. So let's do next. Taking advantage of the linearity property, we can combine two solutions in a special way, and this way is from the linearity property. Look at that, okay? Yeah. All right, so now the combination. All right. The combination, there is a name for it called a linear combination. How about that? Linear combination of two variables, x and y. Yeah. In math, we frequently do this kind of combination called a linear combination. When we need to make a new expression from two variables, x and y, and using the linear combination, we mean the expression is capital AX plus BY. Capital A, capital B, both constant. Okay, AX plus BY, this expression is called the linear combination of X and Y. Here we take advantage, or we just use this way to combine two solutions, two existing solutions. Yeah. Yeah. All right. Yeah. So here you get an idea. Yeah. Why? Yeah. So you may ask, why you use this special linear combination to form a new solution? Because you will see in this way here, capital A unknown, capital B unknown. So any constant A any constant b, if we put it here, we do this linear combination, we will get a new solution. Look at this conclusion. So let me say in this way. Linear combination, capital A, T1 to the kth plus capital B, T2 to the kth will be a new solution for any A and B. Can you see that? Can you see this nice thing? Yeah. The reason behind it, why we get for any capital A, any capital B, we do this linear combination, because if you plug in our original recurrence relation, by the linearity property, this must be a new solution. That's the reason the linearity property is important for this equation. I can show you, this linearity property, I can show you why it is correct. Okay, any linear combination of two solutions is also a solution. Why it is correct. Okay, here we use this property, so this is a property, but you may ask me why it is correct, right? All right. Let me explain a little bit here. All right. Let me use little room here. T1 to the k, that is a solution, right? Equals T1 to the k minus 1 plus T1 to the k minus 2. The first solution. T2 to the kth, the second solution, T2 to the kth, and second solution. Can you multiply the first equation by A, you multiply second equation by B, and adding them together? You can do that, right? First equation, both sides you multiply by A, and the second equation you multiply both sides by B. So you get two equalities, right? So both must be correct. Okay? Two correct equalities. Then you add them up. The new equality must also hold. Okay? That tells you this A T1 to the kth plus B T2 to the kth, it must be a new solution after you add them up. And this only true when the equation is a linear equation. If it's non-linear equation, you cannot do this. Okay? Even if you do this way, you won't get a new solution. Okay? So only the linearity property can preserve that solution property. Okay, all right. So next, we know our new solution takes this form, but capital A, capital B, undetermined. We need to determine capital A and the capital B. So the last thing we need to do, we need to plug in some number, plug in for two cases, base case, n equals 0 and n equals 1, because these two corresponds to the two base cases. So we use the two base cases, we can determine capital A and capital B. So that's the last thing we need to do here. Okay, two initial conditions. So the last step pretty straightforward. So we just plug in and solve the equation, determine coefficients A and B. All right. where n equals 0, yeah. So let's plug in n0 into this formula. After simplification, we get a plus b equals 0. Yeah. So b must be negative a from the first equation. The second one, you plug in n equals 1, you get a1 equals this expression. After simplification, we know its value is 1, the base case, our second base case. Yeah. So after you simplify this equation, but at the same time use b equals negative a. Yeah, so you replace b by negative a and do some simplification, you will get a times root 5 equals 1. So a equals 1 over root 5. Yeah. And the b equals negative 1 over root 5. Then you replace. Now we determine the values for a and b, so you can put them back to the original formula. So we get our Fibonacci number formula. And we know to write the formula, this time we can replace that 1 plus root 5 over 2, the golden ratio expression phi. So, and 1 minus root 5, yeah, over 2, we know the reciprocal way, so it equals negative 1 over phi. Yeah. So finally, the final expression is 1 over root 5 parenthesis phi to the n minus negative 1 to the n over phi to the n. Yeah. Okay. That's the whole discovery procedure. All right? Yeah. Here, yeah, because I give you a long story to describe why we choose that pattern, geometric sequence pattern. Yeah. Yeah. But if you understand this whole story, when you need to solve a problem, so you can just, work on the equation directly, characteristic equation. Yeah. So there is a name, characteristic equation. Yeah. So you solve, yeah, yeah, because people, when they do it, the first step, you start by solve the characteristic equation. For the given recurrence relation, that is, yeah, you can use x. Now, you do not have to use t. Okay, yeah. Characteristic equation from there, yeah, because x squared equals x plus 1. That's the characteristic equation. When you start, you solve this equation. So you have two solutions. Then you use a linear combination, x1 to the nth plus b times x2 to the nth, for your general solution. Then you determine a and b from the initial condition. Okay, determine. The standard way. Yeah. So this is the standard way. Okay. Yeah. All right. So we'll complete this topic. Yeah. All right. So try to understand. Yeah. So I'll give you a long story to help you. Yeah, because we want to understand what's going on. Yeah, behind the special method. Why we do it this way? Yeah, there is some good reason behind it. Yeah. All right. Yeah. So we complete whole module 3. Yeah. Next, I need to move to a new module, module 4. Yeah, another important topic. Yeah. All right. So let me just stop this. file right here and jump to, yeah, this one, module 4. Yeah. Yeah. All right. Okay. Module 4, divide and conquer approach. Another fundamental, very important problem solving method, divide and conquer. Yeah. We used it before, but in this module, so we will learn several different ways to use this divide and conquer approach. Yeah. Part A, insertion sort. Another sorting algorithm, insertion. Special property for this algorithm, insertion method. Yeah. 8.1, insertion operation. Yeah. All right. The problem is our old problem, number 4, sort an array. Yeah. Revisit it. But this time, we will discover some new property, and when we apply this new property, we will have a new solution. So we apply this, our old strategy. So we use this strategy many times before. Yeah. Start with a simple case. Yeah. All right, so now when we start, we consider the data size very small. Okay, the smallest valid data size n equals 1, right? You have one element. When we start, we consider one element array. After that, we grow the data size 1 by 1 each time. Okay, yeah, so we do in that way. Yeah. Yeah. The question, how to connect two adjacent cases? That's actually what we did in module 3, right? Module 3, when we determine the recurrence relation, we use this way. Okay, yeah. So problem size reduction, think about that. Yeah. Here, you know, the reverse way. So we grow the problem size. Yeah. The opposite way of the size reduction. Yeah. But basically the same. Yeah. All right. Working on the problem size in this way, based on our intuition. Yeah. All right. So when we start, we have one element array. It is already sorted, right? One element array, we can treat it as an ordered array. So no problem. Okay, yeah. But the next step, when we have a new element trying to join this sorted array, yeah. So this is a sorted array. But this time, a new element needs to join the ordered array. Then, how do we make A1, put it in the current array and make it sorted, make it ordered? That's what we need to do here. Yeah. By one comparison, you can make it work, right? You only need to do one comparison. Compare A0 and A1, you will get this new ordered array. Okay, yeah, A0, A1. So here you just assume, you know, one is greater than the other, so you get it sorted. So here for simplicity, I just write A0, A1. Okay, yeah. Yeah. All right. Next step. Now, another new element comes in to join this ordered array A2. The question, same question. Yeah. How do we make X2, not A2, we need to do some work, right? Yeah. What kind of work we need to do to make A2 join the current ordered array and get a new ordered array? That question. Okay, yeah. Definitely we need to do some comparisons. Yeah. We can do it, right? After a few comparisons, yeah, actually, the worst case, 2 comparisons. So you can see it. For the worst case, 2 comparisons. For the best case, 1 comparison. Okay, best case, 1 comparison. Worst case, 2 comparisons. You can make it ordered, new ordered array. Yeah. Here we can join X2 with current ordered array in some way. Yeah. So, and you can keep doing things like this. Keep doing, yeah. For this general step, make A sub k new element joining the current ordered array after certain number of comparisons, right? Yeah. So this picture, this diagram gives you a new view of sorting. You can see in this way, you can sort this array, right? Yeah, but it's a new view. It's different from our previous views. Yeah. We took different views before. Yeah. This time we changed to a new view. So this view, you look at the actions you take for each step. Is it insertion step? Insertion? You insert A sub k to an ordered array. Can we see in that way, insertion way? The main step we're using here, just the insertion step. How about that? Okay. This new insertion view will give us a new sorting algorithm. That's the new method. Yeah. All right. Add a new element to the current sorted array and then make it sorted. So that's the typical action we take for each step. And this step. Yeah. So we describe it as insert an element in a sorted array at the right position. You need to find its right position first. Then you do the insertion. Or you just do them together. Yeah, do these 2 things together. Find the location, do the insertion at the same time. Yeah. Yeah. If you figure out the details to do these 2 things, then the sorting is done. The whole sorting is done. Okay, yeah. All right. So let us study this insertion operation. So we call this main step for the new method, insertion operation. Yeah. Let's study the insertion operation. Shift elements for insertion using a diagram to visually understand the step. Yeah. Shift elements to the right. Yeah. How do we implement that insertion operation? Yeah. So this tells us how to implement using some visual way. Yeah. All right, so let me draw the diagram. Okay. So we need to do insertion when we start, we have this picture, okay? Insert AK to ordered array. But you need to find some room for AK, right? Yeah. There, you need to allocate some location for this new element AK. Yeah. But how do you find room for new element AK? Yeah. We use that shift operation, shift to the right operation. Okay. Yeah. Assume this arrow place is the correct place, right position for the new element, AK. We need to locate it and then do the arrangements. Yeah, all right. To do it, yeah, because that AK in the original given array, yeah, that little AK, before we do the insertion, it is in this location. But we need to lift it up, okay? We need to lift it up. That means we do the copy. We make a copy to another variable location. Copy to, so this is a temp variable location, okay? Yeah, temp variable location. So we copy to a temporary location. Yeah. Then after we make that copy, this location is empty, right? Yeah, its original location is empty. So then we can shift other elements to this location. Yeah. All right. Yeah. Then we do comparison with A sub k minus 1. If A sub k minus 1 is greater than A sub k, we shift it to the right vacant location. Yeah, because we already make its right position location vacant. So we shift it. We shift AK minus 1 to its adjacent right position. Okay. Similarly, for AK minus 2, we do another comparison. If it is greater than A sub k, we shift it to its right adjacent vacant location, and so on. Now, keep doing that until after we make this last shift. This is the last shift because we assume this is the right position. Right position. Okay. Yeah. So we stop. After we make the last shift and the A sub k is placed in its right position, then this insertion is done. Yeah, because yeah, although you can try the next one, the next one we assume A next I less than that AK. Okay, so we stop. Yeah. This is the stopping criteria. Stopping criteria. Right? Yeah. Yeah. After that, we do not need to do any comparisons. So we just stop. Okay. So this is the visual understanding of the insertion operation. Okay. Yeah. All right. So then the last one, yeah, because you find the location and you make it vacant, right? Yeah. So this one is available now. Available now, you just copy that temporary location A sub k, that temporary location value to the right position, right location. Yeah, you complete one insertion step. You just repeat this insertion step again and again. You can get a whole array sorted. That's the whole procedure of this insertion sort. Pretty simple, right? Yeah. using your intuition, imagination to understand this procedure visually. All right. So we get this new sorting algorithm. It is called insertion sort. All right. Yeah. So after that, yeah. So the number of assignments, yeah, big theta of k. Yeah. Big theta of k. Yeah. You have the best case, you have the worst case. Right? The best case, one, right? The best case, one comparison. Yeah. After you compare with a sub k minus 1, it is greater than sub k minus 1. So you put it back to its original location. You're done. Insertion completes. Yeah. But the worst case, you need to compare with all the elements in the current array. That's k comparison. Okay. Yeah. K comparison. Yeah. But if we use the asymptotic notation, we can use that big theta of k. Okay. Yeah. All right. Next, 8.2, implementation of insertion sort. Yeah. So the diagram already gives us the implementation idea, actually. Yeah. Here we just do, efficiency estimate. Yeah. How many comparisons do we need? We just count that number. Okay. Yeah. So that's the procedure we need to do. Yeah. The worst case, the total number of comparisons. Yeah. Think about. So when you start insertion from n equals 2 case, yeah, n equals 2 case, you do one comparison, right? When you consider n equals 3 case, insert the last one, you need a 2, right? The first one, you need a 1, last one, you need a 2, and so on, all right? Yeah, until the last one, n case. Yeah, the last one, you need to add this many comparisons. Yeah. So for the total number of comparisons, you need to add all these numbers up. So you get this expression, 1/2 times n minus 1. Okay, yeah. So that is big theta of n squared. Big theta of n squared, yeah, may not be very good, yeah, because for our selection sort, bubble sort, they are both big theta of n squared. Okay. From the asymptotic notation, the same. All these three sorting algorithms belong to the same category, but even in the same category, you can see insertion sort is better than selection sort and bubble sort. So the insertion sort better than selection sort and the bubble sort. Yeah. All right. And best case, yeah, best case, every time when you insert a new element, you enjoy the best case that could happen. That is 1, 1, 1, 1. Every time the new element to be inserted, you only do one comparison, you're done. Yeah. And you have this kind of luck all the way up from the first to the last. All right. That is, you only need to do n minus 1 comparisons. That is big theta of n. So this is much better than that selection sort and a bubble sort. Because for selections of bubble sort, their best case also big theta of n squared. But here, big theta of n. Much better. Yeah. And this property, so here, for this best case, this property, it is prominent for insertion sort. Prominent. Because other sorting algorithms do not have this property. Only this insertion sort has this property. Yeah. So this property is very nice. Yeah. And in the real world applications, we can take advantage of this property. Yeah. So this property could be useful. Later, I will talk about in what situation we can use this property. Okay, yeah. All right. Average case, when you need to do average case, in each insertion step, you need to consider what is the average for each insertion step. Yeah. Then you add that, the number of average comparisons for each insertion step. Add them up, then you get the final average case efficiency. Yeah, it is still in big theta of n squared. Yeah, but approximately one half of the worst case. Okay. Yeah. Yeah. So the coefficient of that nth leading term would become 1/4. Yeah. 1/4 for the average case, not 1/2, 1/4. Yeah. All right. Yeah. How to derive it? Yeah. So here I skip it. Yeah. So you can practice by yourself. Yeah. But the computation is not very hard. Yeah. Not very hard. Yeah. Pretty straightforward. Yeah. All right. Yeah. So we complete this efficiency analysis. Yeah. Yeah. Conclusion. Yeah. So before I finish today's lecture, let's complete this conclusion. Conclusion. Yeah. How to take advantage of that nice property for the best case. Yeah. Best case, this insertion sort performs the best among all available sorting algorithms. Yeah. So we should take advantage of it. Okay. How do we take advantage of it? Yeah. So look at this sentence. If the given array is almost sorted. Yeah. So that's the property of the given array. If the given array has this property, then we should take advantage of this property to do the sorting with the best efficiency. Yeah. Then, conclusion, the insertion sort is a good choice of sorting because we can take advantage of big theta of n efficiency. That is the best thing you can have in all the available sorting algorithms. Big theta of n. Yeah. The best you can have. Okay. Yeah. Let me draw the diagram a little bit. Suppose this is the given data. What do you mean almost sorted? So you have some scattered spots. Yeah. Like this, red circle places the data not ordered. The remaining, most part remaining all ordered. When you have this kind of data, to make it sorted, the best algorithm to use insertion sort. So that is the conclusion we have for this part, for this sorting algorithm. Okay. All right. Yeah. So let me stop. So right here, the next time I have one example, so I want to using the insertion sort idea to solve this simple question.